having just black and white images, as you're probably used to when you think of medical imaging. You think of CT as black and white, yeah, or MRI most of the time is just black and white. But what we actually want is to have information that goes beyond that, so that gives us information about actually beyond just showing where is the cancer, but showing how aggressive is the cancer. But let me just go and expand a little bit from prostate cancer. The role of imaging in the management of cancer in general is a very important role. So we have the opportunity to better understand the biology, having this additional information in the images, to develop new targeted therapies, keyword precision cancer medicine. That's a very hot topic. And how imaging can do this, it can infer and have impact along the whole patient management pipeline. That is, from the first time we detect the disease, the next time when we try to stage the disease to decide is the cancer aggressive or not, and then to prescribe the best therapy, and then monitoring this therapy. So along this whole chain, we want to acquire images as a non-invasive modality and to get the best answers to optimize throughout. So how can imaging achieve impact? Well, imaging can achieve impact if it's a biomarker. And what is a biomarker? A biomarker is a feature that you can extract from the image that is relevant to a patient's diagnosis, that can reliably distinguish healthy from disease tissue. The wish list for good imaging biomarkers is sensitive to the disease, it is specific to the disease and to the aggressiveness of the disease. And it's robust, and one of the points where we still struggle quite a bit in clinical practice is quantifiable. So it's reproducible. It's independent of a radiologist looking at an image. So this is what the engineers want. You want to have quantitative information from the data that we acquire. And importantly, it should be cost effective. So as an example, if you think about the risk of cancer, the aggressiveness of the cancer that I showed you earlier in the prostate example is, first of all, you want to see the lesion in the image. You want it to be sensitive enough that you can see the tumor. But the next is, going beyond that, the details within that lesions can also serve as a biomarker. For example, how perfused is that tumor? How active is its metabolism? Where exactly is it located in the organ? And from that derive probabilities of aggressiveness. So on this image, for example, this is an MRI. It's a morphological image. This is a rectal cancer, and you can see the darker part is where the cancer is. So from this image, you could probably fairly easily derive the size of the tumor, and this is what's mostly done in clinical. You take the size of the tumor, and then the patient gets therapy or comes back, and then you check has it shrunk or has it grown. But imaging can do more than that, and the most potent imaging modality in that sense is MRI, magnetic resonance imaging. So I'm by training, I always did MRI research. It's my favorite imaging modality, and the reason is that MRI is a very versatile imaging modality. And the reason for that is MRI is based on the contrast of the MRI images comes from water in the body, and our body is mostly made of water. Water specifically is made of the protons in the water molecule, and these protons have spin. So we can use its magnetic properties to encode the data, the image data. And because the spin on these magnetic properties depend on the tissue and the surrounding that the spins are in, and this is a very complicated relationship. There's many parameters that we can play with, and this is a very complicated process in the data acquisition of MRI, but it also gives us the opportunity to play around a lot with this and to encode very many different contrasts. So this is just a collection of images of MRI images and the biomarkers that you can calculate from that. So MRI can be purely structural. Here you see some brain images, but it can give you different contrasts of that structure based on how you encode these proton spins in the body. This is not like CT. In CT, you get only one contrast, which is related to the density of tissue. Yeah? Because a purely transmission imaging modality is CT. So CT is stop and go, one image done. Same for PET, positron emission tomography. MRI, depending on how you design your data acquisition process, you get all these very different opportunities for contrast. So you can make MR tractography of the brain, where you can see how the brain is connected. There's this very worldwide, very interesting research project called the Connectome, if you want to Google it. We can encode blood flow. On the top right, you see the cardiac, the heart pumping blood through the aorta, and you can imagine if there's some disease, the blood flow can be inhibited. You can encode that, and many more. So this is what my research has been mostly about, is to use MR physics properties to generate new biomarkers, or to make the biomarkers that we have much more robust. So the tools that I've been using were on the acquisition side, that is programming new ways how we encode this information into the data, playing with these many opportunities that we have in the data acquisition process. At the same time, this is what I would call the extrinsic parameters in my acquisition process. At the same time, modeling the physiology of the body or of the tissue or the organ that I'm interested in. And this is what I call the intrinsic parameters. So this is what we've done traditionally before deep learning came along. We modeled the data acquisition process, we modeled the physiology, and we tried to match the two to derive quantitative imaging biomarkers, to derive new quantitative imaging biomarkers. Moreover to that, we also modeled other things such as motion that appears through the data acquisition process to clean the data or to acquire less corrupted data, and also combining it with other modalities. For example, there's simultaneous PET-MR machines now, for those of you who are a bit into the medical imaging community. And these have challenges to combine the two. So a lot of challenges for MR engineers and MR physicists. The goal was always to get better data faster. And by better data, I mean data that has more information encoded in it about the disease, and to get to that faster and more robust. So when I say I want to have more information encoded in the data, why does this concern you as deep learning experts? Well, if the data doesn't contain in any information of the disease encoded in the signal, you can apply whatever fancy algorithm you want, you're never going to get it out. You know the term legal? Garbage in, garbage out, exactly. So if your data is crap, you cannot do anything. So if your image encoding mechanism is not sensitive enough to distinguish where's the disease and get this disease information in the data, you're essentially lost. So it's where you start with data. Okay, but this talk is a focus on deep learning. So let's look at how deep learning is and has been applied along the imaging pipeline. So the imaging pipeline is the signal processing chain. So this is where we acquire the data, and first the raw data. From the raw data, we need to reconstruct an image. And this is probably, maybe if you're not a medical imaging expert, this is probably what you never thought about. What mostly, if you're from the deep learning community, what you're concerned with is down on this side, in the image analysis side. Saying you have images, and then you're trying to analyze these images. But a lot of interesting stuff actually happens before then, when you're actually trying to get the images. So, and this is very modality specific, yeah. So, for example, in MR, the way we acquire the data, this spin, proton spin data, is in frequency space. So, we're placing the patient into a strong magnetic field, and these spin properties can be encoded one by one. So, this is the take-home message. I mean, the whole process is a lot more complicated than that. But the key message here is, one by one, we have to acquire that frequency data. And then once we have that, we apply just a simple Fourier transform, which is a mathematical operation. You go from this frequency space to image space, and then you get your image data. And the reason, because of that mathematical process here, in MRI, you get two types of data. You get magnitude and phase data. But again, if you're a deep learning expert, and most of the time what you deal with is just the magnitude reconstructed data. Yeah, so, but there's a lot of information, there's additional phase data, for example, that you can use too. In between, there's no other stuff, such as image restoration, such as denoising techniques, accounting for motion, and so on, contrast optimization. So there's other processing steps in between. So there's a lot of steps to get from your raw data that looks like this, which nobody can actually see something. Do you see a cancer in this image? Nothing. You cannot interpret it. So you have to go through a lot of steps in this chain to finally get to your final information that you're interested in, mainly, and that is there disease and how aggressive is the disease? So I said that the take-home message from this side is, let's look at this interesting part where MR physics plays into how we get these images. And where can deep learning help also down here? You've probably seen applications up here, but where can deep learning have an effect in here? Well, first of all, what are the challenges that we're trying to address? And as I said, the most important thing, problem that we have is MRI is too slow. An MRI exam usually takes maybe around 15 to 30 minutes. It can take up to an hour. And during the time, a lot of things can go wrong. The patient breathes, the patient moves, so that all of it contributes to worse data. So we're trying to speed it up, be faster. Okay, so MRI is too slow. So what can we do? Well, as I said, we have to acquire each data in the frequency space one by one. So one obvious solution is just acquire less data. Yeah? So instead of acquiring all the frequency data, let's just skip every second data point. Let's acquire less data. And you can do that in many different ways. You can just sample the middle bit of your frequency data, you can skip every second line, or you can randomly sample data. And this is actually what has been done until deep learning came around. So that's what people have done. We've sampled less, and then we tried to deal with the problems, because there are problems. If you sample less data, because for the experts among you, a theorem that's called the Nyquist theorem is from the signal processing is violated. So you get artifacts. So artifacts means there's some problems in the image. And these appearances of the images, these artifacts depend on how you choose to undersample. Yeah? If you regularly undersample, for example, if you're skipping every second line, you get an effect that is called aliasing. So you have fold over. For example, here you see 3 brains instead of 1. If you're incoherently sampling, this is actually still pretty benign. You can get pretty good images from that. They just appear a bit noisy, as you can see. Yeah? So then research in the years has been mainly around how can I reconstruct good images from these undersampled data. And the way to do this, or the problem was that now the image reconstruction problem, so going from the frequency space to the image space, is an imposed inverse problem. So what we can do to solve this imposed inverse problem is incorporating regularization, and in that regularization, incorporating a priori knowledge. So we're improving our model using a priori knowledge. And this a priori knowledge, there have been 2 schools of research that have been most popular. One is parallel imaging, where my a priori knowledge comes actually from the sensor, how I'm acquiring my signal. So I'm acquiring my signal not with a single receiver, but I have multiple receivers. Again, signal processing people among you probably have heard this concept before. And then I can use the location of this receiver to unfold the problem. So this method of using these additional receivers can be applied for the coherent undersampling to unfold this 3-brain aliasing by using the spatial information. Another technique is compressed sensing, also comes from the signal processing community. It's like JPEG compression. So what you do is you have incoherent sample data, you apply a sparsifying transform into a domain where you have sparse images, and then you can discard the other parts, which is essentially a denoising technique. So the problem with these things is, one, as you can see here, you require additional pieces of hardware. And this is actually when I was in Boston at Mass General Hospital. This was my advisor, Graham Wiggins, and he developed the very first parallel MRI brain coil. This is a 32-channel coil, which is now a product by Siemens. And you can see there goes a lot of time in the lab into this. But this is pretty cool. So you need this additional hardware. But the problem with both of these methods is that we're applying a model. Yeah, we're using a priori knowledge in a model. And here's something that probably you've met in all other domains of your deep learning expertise is traditionally all these models before deep learning came around were probably too simple. Yeah, we could only model certain aspects, and that means that the images that we got from this were not really realistic. So they looked a little bit cartoonish. For example, here in this JPEG compression denoising technique, the image that you get out of this after this algorithm, depending on how you're choosing your regularization, the image can look more like a cartoon. It doesn't look real. So radiologists and clinical practitioners didn't really like these approaches too much. Yeah? So the models were too simple. And this is where deep learning comes in, because deep learning, as you all know, can map very complex solve very complex problems. So this is a very good problem for deep learning to solve. So the question is, can deep learning help in the problem that we're having, mainly going from this undersampled frequency data to get good images by modeling this process? And yes, it can. It's very well suited for that. And it was first introduced in 2016 at NIPS and other conferences. And then since then, there have been multiple solutions for this. And I've shown you some references here. You can look those up in detail. And in the interest of time, I will only go into this very last method, which was published in Nature 2018. And this is a unified framework for image reconstruction. So on the previous slide, all these methods have different approaches to that problem. So some of them are end-to-end solutions. Some of them take the traditional image reconstruction problem that I formulated in the slide before and just use deep learning, for example, to learn the regularization parameters, or to learn the optimization process. So you combine these two approaches. This approach does a full end-to-end deep learning approach. So we have the whole image reconstruction problem is formulated as a data-driven supervised learning task. So we're trying to generate a mapping between the direct mapping between the sensor to the image domain, replacing the conventional stepwise reconstruction chain. And how this is implemented is just a feed-forward, deep, fully connected neural network, followed by a sparse convolutional algorithm. And they show pretty good results for this. As I said, there are other approaches for this, which some reference I've given you in the previous slide. Okay, now let's focus on this second part, the image analysis part. When we're actually having our images reconstructed, and now we're trying to get biomarkers out of this. And the holy grail of quantitative imaging analysis has always been image segmentation. So we want to segment objects out of these images. From them we can calculate further imaging parameters that allows us to quantify the disease in the image. So, and this has been the biggest target for application of deep learning in medical imaging. And one could in principle use neural networks, but the problem is, especially for imaging, there's way too many parameters. So fully connected would be extremely inefficient. So what you want to do, you want to carefully prune the parameter space based on domain knowledge. And in images, this is ideally translational information, so structural information of the images. And here is where convolutional neural networks come in. So a CNN, convolutional neural networks, a particular kind of an artificial neural network that preserves the spatial relationship in the data, and therefore has very few connections with the layers. So we have a lot less parameters to train and are therefore a lot more efficient. So the motivation for this is that we have a repeat structure in other parts of the images. For example, if my convolutional operation is a filter that detects edges, I can detect the same edges in every part of the image with this filter. So I create, in each convolutional operation, I create a feature map, for example, of edges, horizontal lines. And therefore, I can use the same convolutional filters throughout with the same weights. Yeah, so therefore I have a lot less parameters. So let's look a little bit in detail at what these convolution operations are. So our images can be represented essentially as a matrix of numbers. And then what the convolution operation does, it looks at a small part of the image and it calculates based on how this filter or kernel is set up a single number. And then it moves to the next section and repeats the process. And as we go through the whole image, we obtain a feature map. And this feature that we're encoding with this convolutional layer depends on how the filter is set up. So for example, there's on the top right, you can see an average filter, means each entrance, the entrance of this 3 by 3 tensor has the same value. So what you get if you slide this type of kernel through your image, through the input image on the left, what you get is a blurring. And if you now change this, the properties of the filter, for example, looking something like this is essentially like a gradient operation. If the filter looks something like this, what you get then is like an edge detection filter. So if you would slide this kernel through the image, you get an image like this. So this is what convolution operations do in the CNNs. Yeah? So what we create is feature maps from the images. And at the same time, we're downsampling. So we're reducing our complexity, focusing more and more about the features, less about the location. So other building blocks such as activations and the training using backpropagation gradient descent is the same as in other neural networks. One more addition that greatly improved the performance of these CNNs was the use of dropout layers. And what these dropout layers do, during training, they randomly turn off neurons. And what this again does is it reduces the number of parameters, but importantly, it also creates some kind of ensemble averaging. And we all know that this also improves our performance. And I'll show you a second application. Mainly these dropout layers also allow us to introduce uncertainty into these network estimations, which I'll show in one of my research examples later on. So the most common architecture of the CNNs that are used for image segmentations is the UNet. And this UNet was proposed in 2015, and it learns a segmentation in an end-to-end setting. So, and it was very successful. It trained on very few images and won one of the major imaging segmentation challenges. So what the UNet does, the name comes because it's shaped like a U. It has the same input building blocks as the CNN discussed earlier. But importantly, it has this downsampling and then again it's upsampling. So during the downsampling, what we're doing is we're increasing the what. So we're focusing on the features more and more and reducing the information of where, so the spatial or the resolution of the image. In the end, so then you get here your classification of the feature, but then in the end we want some kind of image again, and you want a segmented image. So you have to upsample again to get a reasonable resolution for your output image. And at the end you can see there's the number on the top is the feature number, so you have two output features which with a resolution that is a bit worse than the input image, but not too bad, and you have your segmented image. So this is in a nutshell how the UNet works. So the current state of the art is actually what the authors call the no-new UNet. And this was very recently proposed, only 2020. And the motivation of this was that the authors realized that the UNets, after the introduction of the UNets, there were many different application-specific problems which led to task-specific designs of different UNet designs and configuration. And every time a new paper came out, so therefore they authors emphasized, okay, what we're publishing here is a no new UNet. But rather what they promoted is, rather than promoting a new architecture, they said, okay, we're promoting a pipeline that automates all these decisions about architecture and setup and training. And the implication was that even inexperienced users can use these no-new UNets to get very good results. And already in that paper, the authors showed that it outperformed most other specialized unit deep learning architectures for specialized tasks. So this was a universal solution because of this auto optimization. And how this works, so these authors, they made like a hybrid approach between a completely auto-ML solution and like an expert-driven setup of the architecture. So because the completely auto-ML would have an infinite or very long parameter space to optimize, they started with something that's called like a data fingerprint. So based on the input data that you give to this pipeline, the unit decides on already certain aspects. And then different parameter interconnections are here shown as the gray arrows, are then optimized and chosen based on the combination of the two, the data fingerprint and this rule-based network. Then what you're left with is some fixed parameters, and the unit decides to train 3 resulting architectures with 5-fold cross-validation, and then what is left is actually only to optimize the results from this pipeline fingerprint. So what has been achieved is that we have a very efficient approach to find the optimal configuration out of a very generic setup for any task that you feed to this network. And these are just some of the results. Segmentation of all kinds of organs in medical images, cardiac, liver, lung, and so on, but also on completely different image data such as cells. So very different tasks, same architecture. No, it's architecture optimization pipeline. Sorry. They try not to have the same architecture, but the optimization of the architecture. Okay, good. I'm running out of time. So I wanted to show you 2 research examples. So I'm just going to show you one, I guess. The second one you can, if you're interested, look up on the slides. So the first example was, this work is made done by René Donner, who's a PhD student at King's College London in my supervision. And she now tried to use this known UNet and added some features to get some uncertainty awareness into the segmentation outputs. So she applied this to imaging myeloma, which is a whole body cancer. And the problem is with myeloma is that it's a bone cancer, so it's inside the bone. And with CT, you can see the bone very good. But the problem is the real sensitive good biomarkers are in the MR images. But the problem with bone is not made of water. And as I said, the largest MRI comes from water, so bone in MR is essentially invisible. So we have quite a big challenge here if you want to see biomarkers inside the bone, to segment out the bone. So this problem, because it's such a difficult problem, if you would manually want to do this, it would take an expert 5+ hours. And because it's also so difficult, the input images, there's a lot of variation. So even if a person spends 5 hours, the output will be very different if another person spends 5 hours, another expert spends 5 hours in this. So what we have here is a problem with uncertainty in your labels. So we're trying to train a supervised algorithm, but the problem is that our labels, because of this difficulty of this challenge labeling problem, our labels are highly uncertain. So we have a problem with our ground truth. And we're trying to address this by setting up a network that can also at the same time estimate or take into account this uncertainty. And we have to address 2 different types of uncertainty, the epistemic and the aleatoric uncertainty. One is related to the variation in the observations on your data itself, and the other one simply arises from the lack of data. So the epistemic uncertainty we can address, and I briefly mentioned this earlier, by using dropout as a Bayesian approximation. So the difference is, as I said earlier, the CNN, the convolutional neural networks, already use dropout during training to get this kind of ensemble averaging approach. What we do here now is we're also using dropout during inference, during testing time. And so we're getting repeated predictions T times with a random dropout layout. So we can estimate this epistemic uncertainty as the variance of these t predictions that we're calculating. On the other hand, the other part, the aleatoric uncertainty, can be learned during training if we're having two outputs, not just the mean, but also the variance. And this variance can be trained by modeling in the loss function if we're adding to our output a Gaussian noise with mean 0 and standard deviation of 1. So the difference to the conventional UNet implementation or no UNet implementation is that we have a dropout with probability of 0.15, which is also applied during inference. We're having a loss function that incorporates the variance, and we're simultaneously outputting both the probability and the variance. So at inference time, for each input image, we're calculating t times the probability and variance, t times changing the dropout setup. And then from these final outputs, we generate binary segmentation as the mean of the t probability maps with a certain threshold that can be adjusted. And at the same time, we're getting two uncertainty maps, the aleatoric and epistemic uncertainty, representing from the mean and variance of the second output, the variance. Okay, I will not go into details of the experimental approach, but since we're having a whole body data set, we also were confronted with the decision, how do we feed the data into the network? For example, are we feeding the whole body data? It means we have a lot more data to train with, which is always a good thing for your deep learning. Or feeding with data based on batches so that the network sees more likely data. Yeah? For example, if you're feeding a brain and a leg, these look very different. Yeah? So our idea was to keep them similar with the features, so to achieve better performance. So we looked at which method is better. And then remember, there was this problem with our ground truth. So usually, if you do deep learning image segmentation and test how good you are, for example, you can use a dice score, which compares your ground truth to your output. Now, if your ground truth is off and you're getting something out, we're using the dice score calculating similarity between the two, you actually don't know if you're performing well. Yeah? So we needed a different metric to evaluate our results. So we again asked the radiologists to score the images, the output images, and say, oh, are they actually better than the original input labels? So just a heads up, so you cannot use your dice score. And just to give you the results, so we could get better segmentations using the uncertainty. We could highlight where the network was more uncertain, for example, at the edges, if this belongs to bone or not, and also for areas that are artifacts in the images. And the second part was that when I mentioned the sliding window approach, so not feeding all the data, not inputting all the regions, but having an intermediate input into the data also gave us the best results. And then the next step, what we actually want, is these MR-based biomarkers that you only get after the segmentation. So this whole segmentation process was only an intermediate step, because then we use these segmentations to copy them over to the actual functional information, which is in this case diffusion data, to then decide on what stage the disease is and how it's progressing. But this is still work in progress. Okay, so I think I'll end here, or better, I'll skip to the end. So the second example was in radiotherapy. But what I wanted to show you today is essentially there have been many areas, and I only had time to go into a few, where deep learning can help in the imaging pipeline. There are, of course, challenges and limitations, a lot of them related to the data, a lack of the theoretical underpinnings. So we have a problem with explainability, as you probably have in a lot of domains applications, but in particular in medical imaging. And there's a whole hype around deep learning, but I think it gives us also a chance to unify the two fields of medical imaging and computational approaches, so we can get actually more quantitative biomarkers to improve our patient outcome. So here's a whole set of references if you want to look up more. And I would like to thank my group at King's College in London, who mainly the group of my students who did most of this work. And here's my contact details in case you have questions beyond the social afterwards. Well, thank you very much.
Thank you very much, Isabel. Thank you very much, Isabel. We have time for questions, and yep, available here. We have questions from the audience. Yes, I'm going to come in here with my phone. Fine.
So you said you use Bayesian, basic dropouts to estimate the epistemic uncertainty. I wonder, did you use something like evidential deep learning that also tackles epistemic uncertainty, or any other uncertainty estimation method for the epistemic one? And what were the results? Yeah.
Go back with the microphone.
Very quick answer, no. We haven't used any other approaches or compared them. This is still work in progress. And this was a very natural and easy way to implement, to be honest. But I'm very interested to hear your experiences if there's other ways of doing this.
Yeah. I basically thought that we're going to talk later.
Yeah, there's another question there.
Hi, I have two questions. First, how is the ground truth obtained? Is it by classical signal processing, or how is the ground truth? So the ground truth images on which you train, what are those?
In the myeloma project? In the skeleton segmentation?
For the image reconstruction problem.
Oh, for the image reconstruction problem? Yeah. So, thank you. So the image reconstruction problem was at the beginning of the talk. So the ground truth here is obtained, as I told you, the problem that we were trying to solve is reconstruct from undersampled data. So the ground truth is obtained from fully sampled data. So what is usually done, you have actually a fully sampled data set and you retrospectively discard data and try to get a decent reconstruction from this limited data set that you have. So the ground truth is from the fully sampled data set.
I see. And the second question is, you try to classify these cancer types, or so why do you use this step in between the image reconstruction? Why don't you just classify on the frequency space?
On the directly on frequency space, yes, that would be the full end-to-end pipeline. We're not there yet, but yeah, I'm sure people are working on this. But as you can see, the data doesn't look like anything like images at all. And I'm sure people are working on this, but I'd also like to have a word of caution there. So if you're going that way, because there's one of the biggest issues that we have is an issue of trust. And what all we have in the medical area is computer-aided diagnostic decision support systems. It's all decision support systems, because the end decision is still a human, an expert, a radiologist, or a clinical oncologist. These are the experts who take responsibility for the clinical decision that is made. And they are used and trained to look at images. So I think it's very, even if you think you have a good approach to go directly from frequency space to extract information about cancer aggressiveness, I think it will be very, very hard to get this across in clinical reality.
You can create the images afterwards.
Yeah.
After you get the positives, you create the images afterwards.
Yes, you can create images afterwards in terms of your research process and invalidating your results and then giving it to a radiologist and letting them score similar to what we did. But as I said, there's a whole body of regulatory frameworks that have to go through. Yes, might be possible, will be possible, might be better, but there's just a lot of steps in between.
Because you can only use signal, right?
We have another question here.
I think just add on, perhaps it's good to do end-to-end learning, and you can reconstruct the image later on. So that would be possible too. And you don't lose anything, but you don't need two models. Because you need one model for modeling the image, another model to extract the disease.
Yes.
But you can do it also end-to-end, I think. I mean, it does speak nothing against it to generate the image later on.
Yeah.
But
Yeah, there's a whole box of possibilities here. So how deep learning can be applied? Yeah, so we can have this end-to-end. We can have hybrid approaches, like we said. Okay, we have the end-to-end, then you go back to the images, have a hybrid approach. So the way how you can make deep learning introduced into this pipeline, there are infinite possibilities. But one thing to keep in mind is how we validate, how we trust, and in a sense, how do we convince the people who right now make the decisions, the radiologists, clinical oncologists, to use that technology.
We have one more question here, and then let's take one last one. There.
I also have a question regarding image reconstruction. So you start with these undersampled MRI images. How can you be sure that the deep learning model doesn't hallucinate some perfectly healthy looking structure somewhere where the data wouldn't actually allow you to distinguish this?
Yes, that relates to I think the point that I tried to earlier make, that this information has to be in the data. The disease information, the tumor has to be in the data. If it's not in the data, no algorithm can see it. And that's related to maybe the end-to-end reconstruction is, if there's some disease area, some disease voxel, which essentially was encoded as a disease frequency, is somewhere in the raw data already, we might be able to pick this up using an end-to-end approach. So your question was, okay, if it's not.
Yeah, my question was rather, if you use a classical method, then maybe it looks blurry and the expert would say, okay, I can't really tell if this is healthy or not.
Exactly. So,
and the network would just draw something nice looking.
Yes, but that has also been a problem before when I said, okay, the classic reconstruction problems, they're trying to get information from this undersampled data, they use a priori knowledge. And if you're using a priori knowledge, meaning you're using not disease-specific knowledge. So you might also have exactly that problem that you're masking disease by using a priori knowledge that is related to this parallel coding or to the denoising techniques. And that was exactly the problem that people always had with the acceptance of these earlier techniques too. So you need to build up a lot of trust, and these uncertainty maps outputting at the same time might help you to to direct your focus in areas where the algorithm thinks it is uncertain, but these have to be bulletproof. Yeah.
We have one last question here.
Just one thing more. So making pretty images is not the goal here. Making pretty images is not the goal. We'd rather have noisy, bad images that have disease sensitivity and disease specificity. It's not about making pretty images. This is maybe different in other areas of image computer vision.
Yeah, so coming back to the issues of trust, and besides the uncertainty estimation, has there been any research in causality? I mean, you can estimate the uncertainty, but it's still curve fitting at the end of the day. So has there been any research there, maybe from your group or other groups, and what's the progress in this part?
Yeah, so from my group or from my area, I'm not aware of anything specific. I'm sure there are groups who are working on this, but I'm sure in general this is a huge topic in the deep learning community. And going into explainability, if you go to the language conferences, there's a lot of going on, a huge emphasis on explainability. And one approach is going back to the Bayesian networks, or also going back to the older approaches, symbolic networks and logic-based networks and combine these approaches to get some kind of explainability into this information, than rather having just a pure data-driven approach. Absolutely, yeah. I'm not aware of anything specific to that to work. Certainly, we haven't looked at this yet, but yeah, it's certainly the next step.
Okay, thanks for all these questions and the input there. This shows there's a lot of interest in this topic, and yeah, thank you very, very much, Isabel, for giving this talk. That is highly interesting. So let's give our speaker. So before we go into the break, we have usually a few announcements. Let's do this now. So one thing we pointed out, we want to point out, like there's this URL where we said before there are the slides online of tonight. There we actually have the slides online of a lot of the previous meetups. So usually we collect all the slides of the previous meetups. We have a little gap of last year, but like you get the slides of about 38 different meetups. So if you're interested really in deep learning and topics that we had earlier, because we have quite a broad scope, check out this URL for the past meetup slides. There's also some of the meetups were recorded and are available on YouTube. You'll find the links there too. And in terms of announcements, we often have announcements for events. One thing that we didn't put up on slides now is the largest AI conference in the world, the NeurIPS conference, coming up December 6 to 14. So it's nips.cc. Check out that conference. It's the biggest conference in AI. I forgot to put it on the slides. And another thing is we usually provide everyone in the community the opportunity to announce projects where you look for people or providing job offers for the community, because many people are just out of academia or research and looking for opportunities. So this time it's actually my turn. I have been working for a company called Musimap, which recently got acquired by a company called Utopia Music. Utopia is all about connecting and moving people with music matching. It's a broad topic. We pursue a lot of things. In the end, it's about getting fair pay for the artists in the music industry. You can read this. The company now has about 170 employees and has 4 locations, Zug in Switzerland, London, Stockholm, and Helsinki. There's different domains the company is active. We work with labels, we work with the artists directly, we work with collecting societies. But one topic that is really important for us is music AI. Personally, I have been working in the field of music and machine learning since 2004. And actually, out of the 4 organizers that we organized, these people, all three of us that we're here today, Jan, Alex, and me, we are all working in the field of music and deep learning. So this is a highly interesting topic. We analyze audio spectrograms for different purposes. There's an example here on the top right. For example, we can detect the genre in music, but that's typically a multi-label detection where we detect the intensity of each genre. We do a similar thing for moods, so you know how romantic or sad or melancholic a song is. What's the purpose of this? So first it goes to the labels, but the labels provide this to the big streaming services or the big technology companies such as Amazon. This is just an example here. In the end, the idea is that you can search for music by talking to Alexa, Siri, or Google Assistant by saying, play me a sad, slightly melancholic song out of these genres, not faster than this BPM, for example. This is use cases we can cater to. And how do we do this? With a lot of ground truth, with a lot of training, with a lot of audio analysis. We analyze millions of songs. We have access to really large music databases. And now we're growing heavily and we're looking for new people to join our team. So we are looking for data scientists / AI specialists. I know there's a whole range. As we've seen today, also with different qualifications. The task there would be music tagging, music recommendation. We have other tasks too. What do we want to do with the audio that we analyze? We're looking for data engineers, and we're also looking for musicologists that help us annotate this data. So if you're interested in working in music AI, that's a very exciting topic, as 3 of us here in the room can witness. Talk to me in the break, reach out to me, there's my email, it's also on the portal, or look up that website directly, career.utopiamusic.com/jobs. We do have, so that's for Utopia, you can talk to me in the break or send me an email. We do have another company here tonight that would like to announce a job opportunity. I asked Larissa to come on stage here and present this one.
I'm Larissa. I'm working at the startup called Inspired, and what we are doing is basically we provide the training as an asset for biggest European energy companies, and we trade automatically energy 24/7 at the biggest European exchange. And we want to drive the energy transition, and that's why we want to apply the AI methods to our trading solution. So we are currently growing very, very intensely, and we are looking for different specialists. So we are looking for people who would like to do trading, who would like to do data scientists, who would like to do reinforcement learning, because we want to empower our trading algorithms. And we also have people for IT, like and web development experts. So if some of you are interested in any of these applications, please scan this QR code and check out our jobs. And you also can visit our website, which is inspiredtrading.com. And for more questions, you can always ask me in the break. Thank you.
Thank you very much, Larissa, for this opportunity. All the slides, by the way, are online already. You find all the PDFs of the slides, including those ones. Here is the links to these opportunities. That's almost it for the announcements. Usually at the end of the meetup, we announce the next one. I'm doing this here, this opportunity right now. We are not exactly sure about the date, but hopefully we're going to have the next meetup already on 1st of December, like in 3 weeks. And the topic would be transformer models. Yeah, we need to double check. With this, we go into the break. After the break, stay with us. We have 2 more exciting talks: Trends from Silicon Valley, Deep Learning and Mobility by Georg, and then the hot topics and latest news by Pieler. We're a bit late in the schedule, so let's do 8:10 to continue after the break. This is especially important for the people who follow us online. So bear with us, and 8:10 we're going to continue with the 2 remaining talks. Thank you very much, and see you soon. We have to entertain also our online viewers that are not with us, cannot have the nice conversations here. I hope you had plenty of good conversations. Yeah, we really like to have this as a physical meetup, because one component, of course, are the nice and interesting talks we have, but another one is the really mingling and getting to know new people, getting to know someone who works on a similar problem or can solve that problem that you have. So talking here with each other and exchanging is really an important component of that meetup. So everyone watching online, please consider coming to our meetups in the future. Although right now we don't know if we do physical meetups in the coming months, so we'll see, we will announce it in due time. So, okay, we'll continue here with the 2 remaining talks. Let's go directly to the first one. That is called New Trends and Technologies, Silicon Valley Mobility Innovation. It's held by Dr. Georg Fuerlinger, and he was in Silicon Valley 5 years. He will tell us about this. He was there for the Austrian startups to bring innovation like in both directions, no? Like from here to Silicon Valley, from Silicon Valley to here. That exchange is super important, and he's going to show us what's going on there right now, because with the pandemic, we're also a bit detached on what's going on the other continent. So yeah, let's have Georg on stage with his talk.
Thank you, Thomas. Good evening, everyone, or good morning in Silicon Valley. It's 11:10 over there, 9 hours time difference, so it's good to do this talk now in person in Austria. So we had a lot of webinars that we were hosting, and this 9 hours time difference, not so easy to deal with. Maybe can I see a show of hands who has been in San Francisco, Silicon Valley before? Okay, that's about 15%. Who was in the US before? USA, either coast or central? Okay, that's more than half. Good, good. I think probably not recently, right? But as of 3 days ago, not yesterday actually, the borders are open again. So if you have your vaccination card, you're actually free to travel back to the US again. Just as a short update. For those of you who have not been in Silicon Valley, since for many of probably also of you, Silicon Valley is this kind of myth, or this kind of like word everyone associates something different with it. So I thought I'm gonna bring you a map, or I'm gonna show a little map here. And unfortunately, I don't have a pointer, but so when you talk about Silicon Valley, or like when you think about Silicon Valley, most of the people still associate it with the region somewhere around here. Probably many of you have heard about Stanford University, one of the most renowned universities in the world, or in the US at least. Probably all of you heard about Facebook, heard about Google, heard about Apple. So all of these three companies have their headquarters in Palo Alto, Menlo Park, or in Cupertino. So that's what is also called the South Bay, next to the large city of San Jose, which is actually quite almost double the size of San Francisco, the smaller but better known brother of the two, right? So historically speaking, that's where Silicon Valley kind of like started up or grew up in this region, you know, around Stanford, the companies settled, and Hewlett Packard and all these early stage companies and chip companies, they were all nestled around this Highway 101 over here. But now over the time, and I've spent the last 5 years in Silicon Valley establishing, as Tom said, the office for the Austrian Trade Commission. So our office was situated right on the other side, where you can see the red triangle over there. But it's not that we have been out of Silicon Valley, because now you can say more or less that Silicon Valley is now synonymous for the whole San Francisco or San Jose area, you know. More of the, especially young people, they moved out of this area, they moved out to San Francisco, they wanted to live in a city where there's more happening than just some 1 or 2 bars in this little towns down there. So we saw a strong shift of talent moving up to the city, and the big tech companies and the investors following, and now the whole region basically refers to city. What was my mission there? Maybe in 2 sentences. Tom already said we established the office there with the goal to be the first point of contact for Austrian startups, for companies or universities who want to do business in the region, find partners, investors, or customers. And I handed over now to a colleague of mine, and just arrived 3 months ago back here in Vienna. So very happy to do this first talk here in person. Mobility. Probably not so many associate Silicon Valley with mobility innovation, but this has changed drastically over the course of the last 5 years, I would say. And these are 2 pictures I took just 2 weeks before I left the Bay Area. This one was taken just 5 minutes away from my apartment. Waymo, subsidiary of Google, the leader or one of the leaders in autonomous driving. That's already a generation 3 mobile car driving around there, and you can see how the whole technology stack changed over time. And Zoox, who has heard of Zoox before? Okay, 3 people. The car nerds among you have heard about Zoox. It was just acquired by Amazon, is now part of Amazon, and they're also focusing on self-driving and automated driving. So these are not the only 2 companies in the Bay Area that actually deal with mobility innovation. And so there's no test about this, you don't have to learn all these companies here by heart, but it's just to show you how much innovation and how many companies, research institutes, but also classic automotive suppliers are actually gathering in the whole Bay Area around the topic of mobility. Right, you see some well-known companies like Toyota, Waymo, Ford, Lyft, and so on, but also some smaller companies, and actually in some of those companies are also Austrians are involved. But that's not the topic of the talk here today. It's about mobility innovation. And so why Silicon Valley? the number of new mobility companies really went up quite drastically over the last years. This is a study of McKinsey from 2017, so that numbers have changed now. Long story short, more than half of the new mobility startups in the US are actually not based in Michigan, they're not based around LA, but they're based in San Francisco and Silicon Valley. So there's a lot of innovation happening around those topics. And also when you look at the amount of venture capital invested in mobility companies, the US is still leading the pack in front of China and also Israel. But in these two countries, you have especially two companies that make most of, or that got most of the investment. Lidy, that's the Uber of China, and Mobileye in Israel. For those of you who are really interested in the topic and want to learn more about especially the four big trends in mobility, shared mobility, automatized or automated self-driving developments, electrification, e-cars, and then also connectivity, connected cars. So these are the four big trends that we took a closer look at together with the TOV, the Future Lab. We had a researcher with us for 2 months and compiled this report. So for those of you who are interested to learn a bit more on what's happening in the mobility space, feel free to download this report in German or English. Overall, it's a fascinating time right now, and we've talked to many mobility startups, but also with established OEMs, manufacturers, tier 1, tier 2 suppliers. So the whole ecosystem is shifting, right? We see a lot of new cooperation networks emerging where established manufacturers are actually working with some of these new technology players like Uber and Lyft, right? We're also looking for collaborations with startups. And yeah, so it's exciting, also frightening for some of the established incumbent firms, right? But a lot of this change is happening in Silicon Valley, and I would like to present 3 startups to you today. One of the companies is called Nauro. It's actually founded by an Austrian who left Austria, I think, 20 years ago. He grew up not so far from here, close to Vienna. He's now the CEO of Nauro. They have raised more than 170 million in venture capital from renowned investors. And so what is Nauro doing? They apply deep learning and machine learning to basically help reduce the risk of accidents on the road, to basically reduce collisions and basically coach the driver. How do they do that? They have a little device that they plug under the rear window in the car that basically tracks the environment, what's going on the street and in the surrounding, and they're also tracking the driver. Yes, I know, privacy and all that. In the US, it's not that strict, you can do that. So you attach it in the car and you also monitor the driver. So you can basically see where the driver is looking at, whether he's looking on the road, whether he's texting his girlfriend, whether he's, I don't know, looking out the window for whatever reason he should do it. So they're tracking the driver, and they can detect, based on this image recognition and their proprietary AI, when the driver is distracted and, for example, texting, right? That might not be dangerous, you know, on the highway, every one of us looks somewhere, not maybe straight ahead, certain times while driving. But this becomes obviously dangerous when there is an obstacle ahead. For example, a car that had to brake abruptly, right? Or a kid running on the road. And what the camera does, the outward-facing camera does, basically recognizing when there's problems or when there is certain discontinuities happening on the road, and they can warn the driver when he's distracted. So when the camera detects the driver is distracted and there's a potential for a collision, it will sound an alarm. First, it starts when there's like more time to brake in a very light tone that goes up really drastically and really annoying, so you cannot overhear it, right? And it basically should help the driver to be alert and then handle the situation accordingly. So that's what Nauro does. And but there's an underlying notion here. So that's basically the first way on how they want to coach drivers. They're installing this now in fleets of like transportation trucks around the US and in the coming years around the world to basically coach drivers and see their driving pattern, how secure and insecure they are driving, and basically based on the data they are gathering can really help them become better drivers. But they are also collecting a lot of real world data. Very important data for all these Waymos and Zooks in the world who need this real world data to basically train their AI to become better autonomous drivers. So they are also in talks with many of those companies for a partnership for the data. Now, perceptive automata, I will try to get the video working here for you. It's a company at the Consumer Electronics Show. I learned about them. So they use deep learning and AI algorithm to basically get more human intuition into the machines, into autonomous driving. Sorry. So what does their AI does is basically recognizing, and you see here with the bars, you see, I'll go back here a little bit. Maybe pause for a second. So the AI tries to understand the intention. What's the intensity of the intention that this person will cross my path, right? So one line means okay, there is no problem. The person so the AI recognizes basically the body posture, whether the person is holding something, and really can learn from a wide variety of factors whether there's an intention to cross the parts of the car or not. And the other one is awareness. Does this person see me, meaning the car, right? And that's the green eye here that you can see. So I'm based on these two, and I let the video play now. Based on these two factors, the car, basically the autonomous car, can decide on how it will react on this specific situation. So there's a kid, the little auntie waves to the kid says, hey, hi auntie, I'm not gonna look left and right, I just run over, it's not what we learn in school, but that's what happens, right? So the car recognizes the intention to cross and stops. Cycle is cutting off, you see the eye now, it's red, because now it looks at the car, it has recognized the car, at least the car knows, okay, it has seen me, it indicates it wants to cross, and by then it knows the intention is high to cross, and it does cross. We all know this kind of drivers, right? Especially if you drive at good at night. There's always someone like this, no indicators, but you know by just the behavior of how the car is driving, how it basically behaves, that it's probably crossing the line, and so the car slows down. This is a cell phone user. Okay, there could be some intention to cross because he's close to a crosswalk. He sees me, but he doesn't move. He's just looking on his phone and he's texting. So there is no immediate danger for the car. The car basically doesn't have to slow down or doesn't see any intention to change its course. Right? It's another application how AI can be used to basically increase the safety and security of autonomous driving. Third and last company that I would like to share with you or present to you today is Saildrone. Has everyone heard about Saildrone before? They had 2, 3, 4, 5 people. They had even, I think in Standard or Press, they had a little newspaper article about them. It was one of the best. So part of my job was also to host a lot of delegations, Austrian delegations that came over, and we did a delegation on future of mobility. And I have to say, being at Saildrone, meeting the founder was one of the most inspiring times during these 5 years. Because Richard Jenkins, he's also a world champion in he has the land world speed record with a wind-powered vehicle somewhere in the Mojave Desert. He built his own vehicle and put a lot of sails on there and went up to 200 kilometers an hour, right? But he didn't stop there, but his affinity to sailing and to technology actually led him to found Saildrone. I wanted to play a video to you that explains what Saildrone does, because the gentlemen at Saildrone are much better at that than I am. But unfortunately, we cannot make the sound work because of the Zoom transmission. But at the end, What is Sagron? They have this, maybe I can let the video play and explain it while we look at the video. Or maybe we can try one other thing. Doesn't work, right? Okay. Then I have to try a bad picture. So you can see this, maybe I'll go back a little bit again. So they're based in Alameda in the East Bay, just opposite of San Francisco. They're building these autonomous vehicles. Basically, they are wind and solar powered vehicles. You can see about a little bit longer than a surfboard. And they're drones, basically, sail drones, as the name said. And there's a lot of sensors on there, right? For humidity, for air quality, for everything you can imagine. So it's basically a drifting, autonomous station, weather station, if you will. And they are deployed everywhere in the world to basically map the ocean. Because we have mapped the whole surface of the moon and the Mars, but we only have mapped a tiny fraction of the seabed actually. And Sagron changes that with the proprietary software and AI that they are applying. They have about 4 million pictures of the ocean bed. And so what ImageNet was basically for objects on Earth, right? With all this as the basis, foundation for that, that's what Sagron wants to basically supply for the research on the oceans. So the last part of the video is basically a promotion for AWS because that's what they build on, but we don't need to look at this. So very impressive to see that not only drones up in the sky, but also in the water are basically helping to map the ocean floor. And obviously we want to come up with better prediction models for weather. But also the US Coast Guard employs them to help against piracy or other invasion threats. And maybe one last video. One of these drones actually was deployed right inside a hurricane. I just wanted to show you these pictures because obviously a regular ship cannot go in there, or at least not a manned ship. So that's what it looks like inside a hurricane outside in the Pacific. And that's what you can do with an unmanned drone, basically also measure, take measurements within the hurricane when it is happening. Yeah, I know not a very technical input from my side since I'm not a software engineer by trade, but a business student or a businessman, but I hope there were some insights from, some new insights for all of you. And thank you very much for your attention, and thanks for having me.
Okay, thanks, Georg. Very, very nice. You in Silicon Valley from the distance here. As we have seen, you brought us information about some companies that we didn't know before here. I have actually a first question. We've seen exciting use cases here, companies that went really far. So is it also the other way around that Austrian companies go to Silicon Valley and bring the innovation there or succeed there with exciting applications?
Not only Austrians, but obviously also Austrian companies. I mean, you have been to Silicon Valley with your company a couple of years ago, if I remember correctly. So Silicon Valley is really a melting pot that attracts the smartest and the most motivated people from around the world. That's why by just walking the streets of San Francisco, for example, you wouldn't be able to tell whether you're in Nairobi, in Vienna, or in Brazil, in Rio de Janeiro, because it's really a mix of people similar to New York from everywhere. And it's really a meritocracy, meaning that the people with not only the best ideas, but also with the best progress actually receive funding and get ahead quite quickly there.
So would you still say now in 2021 or approaching 2022, it is a good idea for any company in the world to go there to get this spirit of innovation and exchange with companies there? Or now that we live like in a global world of online information, it's not absolutely required? Or maybe you would still recommend to be there for in the hotspot of innovation?
I think it's still a hotspot and it will remain a hotspot for quite a while, but there was an interesting survey done before the pandemic and after the pandemic, and before the pandemic, they asked young founders, early stage founders, where would you found your company? And before the pandemic, I think 60% said, I want to be in the San Francisco Bay Area, but that was in the US, right? Then I think the next spot was New York, then it was LA, some other big cities, right? During the pandemic or after the pandemic, that switched completely. And yeah, totally remote, I think was just the fourth selection from all these founders. And during the pandemic, that really switched. So about 50 or 60% said, okay, they want to start their company fully remote. Still 20, 25% said they want to start in the Bay Area. And then interesting thing was that not New York, LA or Seattle were then the next cities they want to go to, but it's like these second tier cities like Austin or like Colorado, like Boulder. These were the cities that people wanted to go because they thought it's a better living and price ratio over there. So I think the pandemic has changed a lot, and you see a lot of positions, especially in the US, also promoted as remote, totally remote right now.
Great, thank you. Do we have questions here for this talk, this view on Silicon Valley technology and innovations? No? Yes. So I'm going to start here and then we go over to you.
Sorry, it's a silly question. Did you miss Austrian beer?
Sorry?
Did you miss Austrian beer?
Yes, a lot. I still don't like IPA.
Are you going to remain afterwards for some concrete questions, or do we have to ask them now?
No, I will stick around afterwards.
Because they are a little bit specific.
Sure, we can check.
Great, yeah.
Are there a lot of Austrian companies approaching you for some collaborations or like, as you said, these delegates, like how often does this happen?
I mean, that was my job for the last 5 years, so it happened daily. But now I'm still in touch with a couple of these companies, and currently exploring my next kind of endeavor. But yeah, I'm still in touch with them, and we have a lot of very successful Austrians over there in the Bay Area. That was also our mission, to basically gather them and form a community among them, and it's great to see what they are building over there.
Yeah. Why do you think, or why don't we have a Silicon Valley in Europe? Why do you think?
Some people will argue their city is the Silicon Valley of Europe, right? It depends on who you talk to. There's many answers to that. It's a long answer, but I'll give you a short one. I think Silicon Valley started much earlier than many people think or recognize. It started already in the 40s, right? Even during the Second World War, a lot of technology was developed around Stanford that was needed for the access to win the war, actually. And based on this close collaboration of government, academia, and industry, the foundation was laid, based on which now the Facebooks and Googles of this world basically could further build up, right? But basically the culture of sharing among the three industry types, if you will, and also this very open-mindedness, that's something very particular to California. And yeah, so they have basically some decades head start to some other regions, but we definitely see also what's happening is that the world becomes more multipolar. You'll see more innovation hotspots coming up everywhere. I'm impressed what happened in Vienna over the last 5 years. So it's happening everywhere, but Silicon Valley still has this head start. That's why I think a lot of amazing stuff will come out of this region for a long time.
One more question over here. Yeah.
For this process for Austrian startups that actually want to go to Silicon Valley, they want to seek venture capital, or they just want to do business development there and get collaborations with bigger companies there. What is the process there? Do you have some examples how this is actually working?
Yeah, sure. I mean, what we always told them, the companies don't come too early to Silicon Valley. It's super expensive. It's very competitive, it's very fast moving, so really have to know what are you building, and ideally you already have your customers and your revenue in place, and then go to Silicon Valley to scale, but not necessarily to start, right? So I think that's the most important point. And then it really depends on what you want to achieve, but for example, bit moving. You maybe heard about the company out of Carinthia, Kärnten. They come up there and they did exceptionally well there, but they remained the product development, all the engineering, most of the engineering they kept in Austria. They're still scaling their engineering crowd here in Austria, and they mainly use the US as a sales market and as a business development and investor relations market. And that's a model that we see quite frequently, tap into the great engineers that we have here in Austria. And yeah.
Basically, they get the cheaper talent here in Austria and the venture capital from the US, which makes sense somehow, right?
Cheaper, yes and no. You know the market probably better in engineering here, but the thing is also loyalty. And because when you're an engineer in the Bay Area, you make 150,000 a year easy. That's an entry salary. If you're a good engineer, that goes up to a couple of 100,000 easy a year. But then when Google knocks on the door and offers you 100,000 more a year, most of us probably will get weak and just switch, right? And they don't have competitive clauses in California. So basically, you work for Google, you get an offer from Facebook. The next day, basically, you don't show up at your old job, but you go to the new job because you don't have this competitive clause. And that's a spiral that makes that it's hard to retain the talent. That's why they all have the slides and special kitchens there and massage and all of this to keep the people happy and in the company. But it's really a war for talent.
I wanted to ask about if the company is based in Austria and the sales is in America, what would there be with export issues if the technology can be used as in military areas?
So that's the whole taxing and legal situation is a very tricky one, especially if you do software, because every state has different regulations. So I would strongly advise to talk to a lawyer and a tax consultant before you actually tap in the US market. I'm not an expert in that field. I just know it's a minefield, and you basically want to make sure to deal with that beforehand. And the military question, half of the amount that is invested in R&D is basically from the Department of Defense in the US. So there's hardly any university in the US that doesn't receive funding from the Ministry of Defense. So it's a very influential factor still in the US and in the research landscape over there. And yeah, as a European company, obviously you have maybe other ethical codes that you have to adhere to than American companies, but one of the startups said yes, they're going after the DoD, that they want to have the Department of Defense as their customer, because if you have the Department of Defense as a customer, you have the largest customer in the world, because the budget is so huge, right? So it's also a question what you're going after, right?
Thank you very much, Georg.
Thank you,
Let's give Georg another applause. Hear more in the future. We get to our last talk. That's given by Michael Pieler. I mentioned it. He is a veteran of this meetup and following the topic of deep learning very, very closely. And he's going to show us the latest hot topics, latest news, whatever we call the section. I will welcome you up on stage. I'm going to provide the lecture in a second.
Thank you very much for the introduction. So the two topics I kind of prepared for today were actually lockdown research topic projects on the side, more or less. And let's switch to the slides then, and then it's So the first one is about neural network scaling laws. This is something which is popping up in a lot of applications and fields and data modalities. And the second one is just an interesting application. First, we start with the scaling laws, what is it and why is it interesting? As you can see, this is a figure of, here we have the parameter count and different models released. This is not up to date. If you want the most recent, you can look at this Chronomicon website. They have always an up-to-date list, and what you see here is in the end to show the picture what's happening currently is that they have an exponential trend, and the numbers are increasing fast to very big numbers. And on the top there we have the GPT-3 from OpenAI with I guess you can read it, but it's almost 200 billion parameters, and we will see, like on the last slide, that this is already not the biggest anymore. And the big question is like, why do all the big companies go big for the models? What's the benefit? Because you need a lot of computational power, a lot of GPUs, and yeah, they're not so easy to get them in the first place, but also to use them in a proper way. And there's a very influential paper which kind of looked into the details. It's the scaling loss for neural language models. And what they found out is that yeah, you can scale, or what you see here is the test loss, when you scale the compute used or the dataset size for the parameters. So they look at the factors that could leverage or get to a lower loss. And what they interestingly found is, and this is what you see here, color-coded, and the color indicates the parameter count, and what you see here is that always the bigger model always achieves a lower loss, which means kind of the model can extract more data than a smaller model. So it needs fewer samples to reach the same performance. And this is kind of a very interesting observation because it means the data gets more valuable in the end. You can feed the same amount of data to a larger model, it can extract more information that you can use. And yeah, you see that this is a very nice transition, and you get this very nice aligned curves. And this has some big implications we will later on show. And they of course looked at those three factors, and they looked what gives you the most benefit. And the interesting thing was it's actually the model size. So you can, if you increase your model size, you get the most out of your setup. And this is another paper, and of course the big question is it's on our natural language processing, but does this also hold true for other fields? And there's another paper that looked specifically at the different modalities, and this trend holds also true for all the stuff you see here, like text to image, video, language, math, images. So this seems like a general trend. And I guess we will see more of those scaling laws setups and tests in future publications, as this will be also kind of a way to set up for the model class. And like this is, I don't know when this text was written or this article, but this is kind of a very influential one. And yeah, some people I know would even say you should always read that or reread it every 6 months because it's always getting truer. And in the end, kind of the bitter lesson condensed is usually if you can scale a very like simple logic to very big degrees, this is usually also always what wins out. And this is especially true for search and learning, which is of kind then relates to deep learning. And I can highly recommend to have a look at this bitter lesson. It's also, I don't remember the name now, I guess it's the famous reinforcement learning professor who also wrote it. And the big question is now, okay, we know those models scale very well, what should we do actually with that finding? And before that, this is something I saw today. Maybe try the other microphone that might have ended up with better. Yeah, so the summary slide is next one. This is actually one I put in today because I was looking at this NVIDIA GTC conference, and yeah, I guess it kind of perfectly fits to the topic. And what you see here is this scaling, so those are like the most recent numbers. This Megatron Turing model is like more than 2 times bigger than this GPT-3, and the trend seems to continue. But what I liked about this image, this is why I put it there, is usually you always like have this comparison to Moore's law, where you see doubles every 2 years, but especially for those huge transformer models, you have like more than 200 times every 2 years. The factor of increase, which I found very interesting. I mean, this is of course very interesting for NVIDIA because there's a lot of GPUs, but yeah, also the results. Somebody has to pay for that and it has to make sense. Yeah, what are the implications in the end, which is also kind of the summary. Large models seem to be very sample efficient, and so when you have a compute budget, the best thing is to spend it on the biggest model possible. And showing it for one epoch, which is the last point, and I find it very interesting because usually we always talk about, yeah, between a couple of epochs, the model sees the data almost like in a very similar way again. But for those huge language models, this is actually not true anymore, because you have so much data actually. For those language models, one of the biggest data sets is around 800 gigabytes, so you can hardly show the data to the model in 100% way. And yeah, this the second last point, and this is actually also what is maybe good or good for the big players, but maybe bad for the not so big players, is due to that kind of larger models are more sample efficient, data is maybe not an issue anymore at one point. Those big models can be a very important thing in the future, because maybe the person or the company with the biggest model is maybe then winning everything, the other ones are maybe then losing out. But let's not hold that, but those are kind of the implications by those Lewis-Steven laws. And in the end, I put my lot of slides together, but there's also a very short summary, which, yeah, seems to be still true. Let's see how this goes on. Especially the light the axis here, which says layers over layers. Yeah, if you're interested in kind of large language models transformers, I can highly recommend the Fuerlinger research group. This is kind of people that found each other on the internet that luckily got a lot of compute. So if you have an interesting project, you can try to propose it there and maybe give you some GPUs. This is also where I found about those Lewis-Steven laws out the first time. And also this G-word blog has a very detailed overview of the topic. A lot of very interesting thoughts around that. This is also highly recommended. And other things are also very, very good if you're interested in that. And the second part, or this is kind of a smaller part of the hot topics. I presented long ago, I don't know, when Clip came out, there was a short introduction, and Clip is like a model that you can use text and images and get a combined embedding space that is very powerful. And what we see, or what I will show you also on the next slide, is those the Clip models that were open available, and you can download them, and people start to play with that now to find a lot of interesting applications. And this is one that I like a lot. I don't know this capture solvers. This was something I guess you could not do 2 years ago, but I'm not 100% sure. But with a ready-to-use Clip model, this works right out of the box with a simple logic, which I found also very amazing. So this will be something that will maybe also change in the future in order to be still usable, to detect humans from non-humans. And the other thing, this is what you see on the other side, what I found very interesting is what they did there. They took a very, maybe not basic, but a very, deep learning algorithm to identify regions of an image. Then they simply prompt those regions and run it through a Clip model with a set of text prompts. So you could, if you want to do object detection, I don't know, for plants, television, or couches, you would hand over those texts. It's always the same model, so you can exchange those. If you're looking for, I don't know, cats, you simply hand over the class cat. And this works amazingly good without ever touching the model or retraining it right out of the box. You can actually download the model and set up your own object detection system in kind of 5 minutes, which I found very interesting because this is something you could not do 2 years ago. And this is more like an interesting art application of Clip, and I find the idea very interesting because what they use here Clip for is actually as a loss or as a kind of a guide to steer a model. And you have here some kind of model that creates an image, doesn't matter how this is set up. And then you can use the Clip model. You can also use a text prompt again, where you can say, I don't know, I want a picture with the style of whatever artist, and with that kind of embedding similarity measurement, you can guide the generating model into a direction that you want, which I find very interesting. So you have kind of a way that you can use text to guide the generation process. And this is like a similar application, which is maybe easier to understand from the figure here, where you have like they use your frozen model and the one that is trained, and you have here this text prompt. So the first one is a photo, and then you have you train a second model to create a specific style. And this example is anime painting, and then you can use clip as a kind of a loss to train this model, and this model then can take in realistic photos and gives you this painting, which is also a very interesting application. Nobody has sort of 2 years ago did this something. And yeah, with that, I'm actually at the end. I hope you, sorry.
Thank you, Michael, for this collection of hot topics, very interesting each time. We're currently planning of doing a special edition actually on transformers. Still need to figure out when. That's going to be interesting too. For tonight, yeah, let's do a few last questions if there are any for this section, for this last talk. Anything? Yes.
I just have a comment on the recapture solving. So a colleague of mine saw that sometimes some of the images are now generated by a generator reservoir network. So it says select all images with a truck, and then there's something that would probably look like a truck to a neural network, but as a human you can see it's kind of broken.
Okay. So maybe that was like
okay, no, that's an answer.
Yeah. That's interesting, yeah.
Any other question? Okay, then yeah, thanks Michael again. This concludes our meetup. Please watch our meetup.com page, or if you signed up anyway, you get our announcements when we announce another meetup. We have maybe date for 1st of December, let's see. For tonight, we can still stay here till 9:30, so I think we've got another half hour to mingle a bit more. There were a couple of questions I think you had directly for the speakers. All of our speakers are still present. We are all present as the organizers and also the ones who announce jobs. But feel free to approach also people that you don't know yet. Ask them what they are working on. Maybe they have interesting input for you. Yeah, also thanks a lot for everyone that has been here, but also for the people who watch us online. We realized today that we didn't provide any possibility for the people online to ask questions. We're going to improve on that next time. But yeah, thanks everyone. Hope to see you next time again. And yeah, here we can enter to the last networking part. And yeah, see you soon.